All right, so I wasn't planning to do this until a little bit later, but Drew Springer Miller was being so difficult that I had to do it right now. It's not even the end of the school day, and I'm squeezing this in between classes because she's so demanding. So we're going to talk about aerobic respiration, at least the first half of it. And in particular, we're going to focus in on, and don't forget that this whole area over here is the aerobic side, meaning that you have oxygen available. Aerobic, or aerobe, means oxygen, so anaerobic without oxygen, aerobic with oxygen. And you're going to pump in the same single glucose into this process. You're going to go through glycolysis, then the prep steps, and Krebs cycle, electron transport, phosphorylation. But today we're just going to focus in on, actually we're not going to do much in the way of glycolysis because it's the exact same glycolysis that you saw with anaerobic respiration. We're going to start with prep steps and then talk about Krebs cycle. Okay? So don't forget, let's actually move on to the next thing, a couple things here. Hold on. Here we have glycolysis. I'm not going to go over this all over again. What I want us to focus in on, though, is that the end point of glycolysis is that you produce this pyruvate, or these two pyruvates. You also produce 4 ATP, but don't forget, you use 2 ATP, so it's a net gain of just 2. 4 minus 2 equals 2. And you also produce NADH. Now, unlike the fermentation pathways, whose sole focus was to regenerate NAD plus from NADH, we now like NADH, and we want to keep it the way it is. So we want to generate as much NADH as we possibly can. So staying with this at the end of glycolysis and keeping it as an NADH is a good thing. But these two pyruvates still have a lot of energy tied up in them, and it's what we're going to do with those two pyruvates that becomes important. So let's start off with what are called the prep steps of the aerobic respiration pathway. All right, so here we have a pyruvate, and I should actually probably write the word pyruvate so you don't forget this. And in fact, it's not just one pyruvate. We're going to say that we have, all right, so we got 2 pyruvates coming into this. And these pyruvates just were created through glycolysis, and they're immediately going to go cruising into the mitochondrion. Okay, so they go inside the mitochondrion, and it's inside of the mitochondrion where these things called the preparatory steps take place. And I'm just going to say from now on they're called the prep steps. It makes it a lot easier. And so the prep steps are going to be something that happen to these 2 pyruvates. So let me just, I'm going to start putting some details about a reaction that's going on inside of here. So we're going to take these 2 pyruvates. Let me go ahead and select these guys. Copy them up. Move down here. Oops. Paste them. And we're going to combine those with something called coenzyme A. So we're going to take 2 coenzyme A's, and in fact, I'm going to abbreviate coenzyme A. Instead of calling it coenzyme A, I'm just going to call it CoA. Makes it a lot easier to fit everything in here. We're also going to add in a couple of NAD pluses, and these NAD pluses are cruising around, found floating around in the mitochondrion all over the place. And those things are all going to combine to form something called acetyl-CoA. Acetyl-CoA. So let's see, I need to grab 2 of these. Will this work? Let's see if it does a partial. I'm going to be bummed. Oh, it does a partial. Hold on, let me get it fixed. Hold on. Okay, so you can see here in this process, we're going to create a 2-carbon compound, 2 2-carbon compounds, 2 1-carbon compounds, and 2 NADHs from these original reactants. So let's go ahead and name all these things once again. I'm just going to zoom in here. Let's go purple here. These are the pyruvates. These are the coenzyme A. These are NADs, NAD pluses. We don't need to name those. But these guys down here become, when they lose electrons and protons and one of the carbons, as well as an oxygen, these become acetyl-CoA. Okay, and then these guys right here are actually carbon dioxide molecules that form. And then lastly, you form NADH. Okay, now don't forget that this is going to be an important thing. I want to now, as much as possible, I want to generate as many of these NADHs as I can create. So that means I've just produced from 2 pyruvates 2 NADHs, and that's really useful. But we're not done, because then we move in from the prep steps, we move into the Krebs cycle. And don't forget, I'm not going to ever have you try to memorize these things. I'm going to provide this all to you. You just have to understand how to interpret what's going on with these reactions and these schemes that I'm building up here. So the thing that's actually specifically that's going to go into the Krebs cycle are these 2 acetyl-CoAs. So perhaps really what I should do is grab up this arrow right here and point it, well, I don't know if I can rotate it. There we go. I can point it in this direction towards our Krebs cycle. Because the other things, the CO2, for example, is going to be a waste product that you eventually breathe out if you're a human being. And then you'll see, I'll tell you more about the fate of the NADHs later. Okay, so we take these 2 acetyl-CoAs and we're going to pump those into this thing called the Krebs cycle. Now you're going to need a little bit of room here for the Krebs cycle. In fact, I'm going to go on to another page to do this just because I want to be able to take up the entire space. The Krebs cycle does have a different name to it as well that you might see, and that is called the citric acid cycle. But it is a cycle, just like what we saw with the Calvin-Benson cycle, so it's going to loop around on top of itself. So let's take a look at the Krebs cycle. Okay, so we start here with our acetyl-CoA. Now, it's important that you focus in on the fact that I just now took 1 of these acetyl-CoAs. So we're just going to watch what happens to 1 acetyl-CoA. Know, however, that there eventually there's going to be another acetyl-CoA that comes into this because, just as we showed back here, we produce 2 acetyl-CoAs in this reaction. So first, just take 1, and let's go see the fate of 1 of these things, and then we're going to just repeat the whole process for the other guy. So we have this acetyl-CoA, and this brings us, oh, actually, whoops, back that up, undo. Okay, the acetyl-CoA is going to combine with a 4-carbon compound. Okay, so let me make that, hold on. Okay, so the acetyl-CoA is going to combine with 1 oxaloacetate. And you'll see that oxaloacetate is something that's going to be coming up from below in our cycle. And when it combines with the oxaloacetate, the 2 things come together to form a 6-carbon compound. And that 6-carbon compound is called citrate, which is why this is also called the citric acid cycle, because citrate in certain conditions becomes citric acid. So there you have the citrate that forms. And citrate is actually a pretty mellow thing. It likes to hang out and continue to be citrate, and it's comfortable doing that. But unfortunately, it can't stay that way because we want to mess with it and we want to extract some energy out of this. So in fact, we perturb it. We perturb it by bringing in our favorite thing that always perturbs things. Let's go way back here. Remember how we got this whole reaction to take place? I said that there was a key to this, as you can see right here. And that key, in fact, was this dude, NAD+. NAD+ is a rascal. It goes in there and it messes with everything. And that's exactly what we're going to see happen for our citric acid cycle, because we're going to bring NAD+ into this reaction as well. And when the NAD+ comes into here, it causes a whole change in the whole citric acid or citrate molecule. And in fact, what comes out of that is it causes one of these carbons to snap off the citrate. And in fact, when it releases, it takes away an oxygen with it, and so what we have here that's being lost is a carbon dioxide molecule that then you breathe out if you're a human being. Okay? Now, in the process of doing that, the NAD+ is going to also steal up a couple of electrons and a couple of protons. So in fact, we do exactly what we wanted it to do, which is this reaction leads to the production of a fresh and happy NADH. And don't forget, this NADH is something that we now like and want to collect. Okay? So, what happens next? Let's take a look. You can see that since we lost a carbon, we now have a 5-carbon molecule. And again, it's sort of settling down and thinking that all is well, and then the gadfly comes in again. Another one of these NAD pluses comes cruising in here to mess with everything. And this leads to the exact same situation that we just saw moments ago. So we produce another carbon dioxide, and as a result of this, we also are going to produce another one of these NADHs. And again, we're happy about that. We like collecting up these NADHs. And of course, if we go through this process, we've just lost another carbon, so we're going to produce a 4-carbon molecule. Now, this 4-carbon molecule doesn't really like its situation. In fact, it has a lot of energy associated with it, and we take advantage of that. We mess with it. And through a complicated set of reactions that involve a whole bunch of enzymes, we actually bring in a couple of ADPs and a couple of P sub i's, or actually one, I shouldn't say a couple of. All right? And as a result of interacting with that 4-carbon molecule, we have a substrate level phosphorylation that's going to take place to produce an ATP molecule out of this. All right, so we get sort of a free ATP molecule from this reaction that occurs here at the bottom of our Krebs cycle. And I'm going to box that up in red because, remember, that's really what we're trying to do here. We can't forget, there's so many complicated details that are going on. We often forget that the whole point of aerobic cellular respiration is to produce ATP. So indeed, there we have it. 1 ATP is produced in the part of this Krebs cycle. Now you can see that I just completed this cycle because we actually have a 4-carbon molecule right here, and we need to end up with a 4-carbon oxaloacetate. But you should understand that oxaloacetate is a really low energy, low potential energy kind of molecule. And this dude down here, who's got no name, this 4-carbon molecule, it actually has a name, I'm not going to give it to you though, still has a lot of energy even after it does the substrate level phosphorylation to make ATP. And it still has a lot of bits and pieces associated with it that can be used in reactions, and that's exactly what happens. What we do is we bring in another one of these NAD plus like things, but it's not NAD plus. Instead, it's FAD plus. And as a result of interacting, meaning stealing away electrons and protons from that 4-carbon molecule that is hidden right over here, you can sort of see it off screen for a little bit, it turns into something that's super useful, FADH2. And I'm going to box that guy up in red because just like our NADHs, our FADH2s are incredibly important. I should have written it in black. Whoops, sorry. And then lastly, before it turns into oxaloacetate, we're going to take another NAD+. Again, they're floating all over the place. And as a result of the NAD+ interacting with this 4-carbon molecule, then this becomes NADH. Box that up in red. And then the molecule can return to becoming an oxaloacetate, which will then continue the cycle by combining with an acetyl-CoA. So out of this whole thing, you can see that from one pyruvate, you produce 3 NADHs, 1 FADH2, and 1 ATP. But we have 2 acetyl-CoAs that come out of this. So that means from our 2, let's just tally this up. Our 2, where's back up? Where's undo? There. Okay. From our 2 acetyl, oh, that's still not going to work. 2 acetyl-CoAs, okay, we produce 3, oh, Chang, sheesh, produce 6 NADHs, 2 FADH2s, and 2 ATP. We also produce, and I'm just going to put this in parentheses over here, we produced 4 carbon dioxide molecules. I put it in parentheses or brackets because that's a waste product. We don't really care about that stuff. We care much more about the NADHs, FADH2s, and ATPs. Now, don't forget that in the prep steps that we did right over here, we also produced 2 NADHs, right? And also, if we go back to our glycolytic pathways, we also produced 2 NADHs from 1 glucose molecule. So we're starting to compile a bunch of NADHs, a few FADH2s, and a couple of ATPs, because don't forget we also produced ATP in glycolysis. All right, stopping there.